Why is it that when you look in a mirror, your image appears to be the same distance behind the mirror as you are in front of it? Most people don't even think about this. They just accept it. But let's think about it carefully. There's something very peculiar going on here. Light from your face goes to the mirror, and then it comes back to your eye. But where did that light go? Is there actually a copy of you behind the mirror? Of course not. So what's really happening? Now let me tell you about a principle that I think is one of the most beautiful things in physics. It's called Fermat's principle of least time, and it was discovered, or really invented, by a French lawyer named Fermat around 1650. Fermat asked himself, among all the possible paths that light could take from a source to a destination, which one does light actually choose? And his answer was surprisingly simple. It chooses the path that takes the least amount of time. Now I know what you're thinking. How does light know which path is the fastest? Does it try all the paths first? That's a wonderful question, and I promise I'll come back to it because it leads to something really profound. But first, let me show you how this principle explains reflection. Imagine you have a light source on one side of a mirror and your eye on the other side. Light leaves the source, travels to some point on the mirror, and then bounces back to your eye. Now there are infinitely many points on that mirror where the light could hit, but light doesn't go everywhere. It goes to the point where the total travel time is shortest. And here's the beautiful part. When you work out the mathematics, when you find the point that minimizes the travel time, something remarkable happens. The angle at which the light comes in equals the angle at which the light goes out. The angle of incidence equals the angle of reflection. This isn't just an arbitrary rule that someone discovered by experiment and decided to memorize. It's a consequence of a deeper principle. It falls out naturally from asking, what path gets light from point A to point B in the least time? The answer is the path where the angles are equal. Now let's think about this more carefully because there's something even more interesting here. Why does light follow this path of least time? What force is pushing it in that direction? Well, here's the strange thing. I can't answer that question in the way you probably want me to. Nature doesn't work that way. We don't know why light chooses the fastest path. We just know that it does. And whenever you ask why in physics, you eventually come to something that you can't explain further. You have to accept it as a basic principle. But let me tell you about something even stranger. And this is where things get really interesting. The principle of least time actually comes from a much deeper principle in quantum mechanics. It comes from what's called the principle of stationary action, or sum over histories. Richard Feynman, and I know we're talking about Feynman's ideas, so I should mention this. Feynman showed that if you think about light as being able to take every possible path between 2 points simultaneously, and if you add up all these different paths, weighting them by their quantum phases, the only paths that survive and add up constructively are the ones near the path of least time. In other words, light doesn't choose the fastest path because it's checking the time. Light explores all possible paths all at once, but only the paths near the classical path of least time reinforce each other. The others cancel out. So the practical result is that light behaves as if it's following the fastest path, but that's really just what happens when you add up all these quantum possibilities. Now you might be wondering, what exactly is light? Is it a particle or a wave? And the answer is yes, and that's not a joke. Light is both. This is one of the most confusing aspects of quantum mechanics. And I'll be honest with you, at some level, nobody understands it completely. But let me try to explain what we do understand. Light comes in packets of energy called photons. Each photon is associated with an electromagnetic wave. When you have many photons all moving together in the same direction, they act like a wave. But when you look very carefully, you see that light is made of individual photons. The duality between particle and wave is not something you can visualize by imagining that light is somehow a little bit of both. It's stranger than that. It's that light behaves differently depending on how you look at it. But for understanding reflection, what matters is this. Light doesn't bounce off a mirror the way a ball bounces off a wall. That picture is completely wrong. Here's what really happens. When light hits a mirror, it interacts with the electrons in the metal. Now, a metal like silver or aluminum has what we call free electrons, electrons that aren't tightly bound to any particular atom. They can move around relatively easily. When an electromagnetic wave hits these electrons, it makes them oscillate. These oscillating electrons are accelerated, and when you accelerate an electric charge, it creates a new electromagnetic wave. So the reflected light isn't actually light bouncing off the surface. It's new light being created by the oscillating electrons in the metal. This is an important distinction. The light that you see reflected isn't the same light that came in. It's newly created light produced by the oscillations of the electrons. The incoming light drives the electrons, and the electrons generate new light. And due to the constraints of how the material is structured, this new light comes out at just the angle where the angles of incidence and reflection are equal. Now, why is this? Why do the electrons respond in a way that creates light at this particular angle? That's a question that involves the detailed physics of how electromagnetic fields interact with matter. It's not trivial, but the basic idea is that the electrons feel the electric field of the incoming light wave. This causes them to oscillate. And depending on the properties of the metal, the constraints of the boundary conditions at the surface, and the wave properties of light, the electrons oscillate in such a way that they send out new light at the reflection angle. This is all classical physics, or at least it can be understood at the classical level using Maxwell's equations and the motion of charges. But here's what's fascinating. When you look at the same thing from the quantum mechanical perspective, using quantum electrodynamics, you get the same answer. The laws of reflection emerge naturally from quantum mechanics too. In fact, let me tell you about something even more peculiar. In quantum electrodynamics, what actually happens is that a photon doesn't exactly get absorbed by an electron and then spit back out. Instead, at the most fundamental level, a photon and an electron interact through the exchange of virtual photons. The photon scatters off the electron. And when you have many, many electrons all doing this scattering simultaneously in a metal, all these individual scattering events add up. The result is the bulk behavior that we see, reflection. Now, you might think that this means the laws of optics are going to change at the quantum level, that there are all kinds of subtle quantum effects that mess with reflection. But here's the wonderful thing. At the scales we usually deal with, the quantum effects average out. The reflection law emerges unchanged. When you look at a macroscopic mirror, it follows the classical laws of reflection almost perfectly. But wait, almost perfectly? What do you mean almost? Well, let me tell you about some of the complications. First, not all the light gets reflected. Some of it gets absorbed by the metal. The electrons in the metal don't just get pushed by the electric field and then pushed back. They also lose energy. When an electron oscillates, it radiates some energy away. In a conductor, some of this energy goes into heat. This is why mirrors aren't 100% reflective. They absorb some of the energy. The amount of light that gets reflected depends on several things. It depends on the wavelength of the light. It depends on the angle at which the light hits the mirror. And it depends on the material of the mirror. A silver mirror is different from an aluminum mirror, is different from a dielectric mirror. Each has different optical properties. Let me talk about that last one because it's interesting. A dielectric mirror isn't made of metal at all. It's made of alternating layers of non-conducting materials, insulators. Each layer has a different refractive index. Light bounces off the interfaces between these layers, and by carefully choosing the thickness of each layer, you can make the bounces interfere constructively in one direction and destructively in another. So you can create a mirror that's highly reflective for some wavelengths and transparent for others. It's amazing. You can even create a mirror that reflects only one color of light and lets all the other colors pass through. But here's the crucial point. Even in these dielectric mirrors, the fundamental mechanism is the same. Electromagnetic waves interact with the electrons in the material, causing them to oscillate. These oscillations create new waves. And due to the principle of superposition, the fact that you can add waves together, the total wave that emerges is different from what you'd expect if the light were just passing through. The interference of waves at different layers, all oscillating slightly differently due to their different indices of refraction, creates the reflection effect. Now let me go back to something I mentioned earlier about quantum mechanics. I said that light takes all possible paths simultaneously. Let me explain this a bit more carefully because it's really the key to understanding quantum reflection at the deepest level. Imagine you have a light source and a detector. In the classical view, light travels in a straight line, goes to the mirror, reflects at the correct angle, and hits the detector. But in the quantum view, the path integral view that Feynman developed, light doesn't travel in a straight line. The amplitude for light to travel from the source to the detector is actually the sum of the amplitudes for light to take every conceivable path between them. Every path contributes. Every possible way the light could wiggle and jiggle on the way to the detector, they all contribute. But here's the key. These paths have different lengths. A longer path takes a different amount of time than a shorter path. In quantum mechanics, the amplitude for each path has a phase associated with it. This phase is related to the time the path takes, or equivalently, the optical path length. When you add up all these amplitudes, the ones with similar phases, the ones that take similar times, they all add together, reinforcing each other. But the ones with very different phases, they cancel out. They interfere destructively. What's the result? The paths that add up constructively are the ones clustered near the path of least time, the classical path, the path where the angle of incidence equals the angle of reflection. That path and all the nearby paths in the quantum phase space, they all have nearly the same phase. So they all add up together. But paths far away from the classical path, they interfere with each other and mostly cancel. This is profound. It means that the classical law of reflection isn't just an approximation. It's an exact consequence of quantum mechanics in the classical limit. When you do the sum over all quantum paths, taking them all at once, the result is that light behaves classically. It follows the classical reflection law. Now this leads to an interesting question. What is light really doing? Is it following the law of reflection, or is it exploring all paths, and they just happen to work out so that the classical path dominates? The answer is both, or neither, depending on how you want to think about it. The mathematical description is unambiguous. The interpretation is a matter of philosophy. And I'm not a big fan of worrying too much about the philosophy. What matters is that we have a description that works, that predicts the right answer. But let me tell you something else interesting. There are situations where the classical prediction fails. There are situations where light can go in directions where classically there should be no light at all. For example, there's something called quantum tunneling. A quantum particle can sometimes appear in a region where classically it shouldn't be able to go. Light can do similar things. If a barrier is very thin on the order of the wavelength of light, light can sometimes leak through, even if classically it should be totally reflected. I mentioned this earlier with mirrors. If you have total internal reflection at the interface between two materials, if a piece of glass is up against another piece of glass with just a tiny air gap between them, something remarkable happens. Even though light is totally internally reflected from the first glass-air interface, the quantum wave doesn't stop there. The wave amplitude decays exponentially in the air gap, but if the gap is very small, the amplitude is still significant when it reaches the second piece of glass. So even though classically there should be total reflection, some light leaks through. This is a beautiful example of a quantum effect that has no classical analog, but it still obeys the same fundamental principle. The quantum electrodynamics is describing what really happens, and the classical laws are accurate in the limit where wavelengths are small compared to the size of the apparatus. All right, so now let me bring this all together. You ask me what happens when light hits a mirror. Here's what I'll say. Light, which is fundamentally a quantum phenomenon, an excitation of the electromagnetic field, interacts with the electrons in the mirror. These electrons oscillate due to the electromagnetic force of the incoming light. The oscillations create new electromagnetic waves that propagate back out into space. The direction of these outgoing waves is constrained by the properties of the material and the wavelength of the light. For a smooth mirror surface, the result is that the new light emerges at an angle such that the angle of incidence equals the angle of reflection. This law of reflection can be understood from multiple perspectives. From the classical perspective, it emerges from Fermat's principle of least time. From the quantum perspective, it emerges from the path integral formulation, where light explores all possible paths, and the classical path is the one that survives due to constructive interference. Both perspectives are correct. They're describing the same phenomenon at different levels of approximation. But here's what I really want to emphasize. The image you see in a mirror isn't coming from behind the mirror. There's nothing actually back there creating your image. The image is a trick of optics. It's created by the fact that the light coming from your face has been reflected in a way that your eye interprets as coming from a point behind the mirror. Your brain uses the law of reflection, angle in equals angle out, to trace the light back to where it would have come from if the light had traveled in straight lines. And your brain concludes that there's an image of you behind the mirror. Now, there's something else I should mention because it gets at a deeper layer of the physics. I've been talking about how the electrons in the metal respond to light, but how exactly do they respond? What determines whether an electron is going to oscillate in a way that creates a strong reflected wave or a weak one? This gets into the quantum description of how electrons interact with photons, and it's really the domain of quantum electrodynamics, the theory that Feynman basically invented. The interaction between a photon and an electron can be represented by a Feynman diagram. An electron absorbs a photon and emits a photon, or the photon splits into an electron-positron pair and then recombines. There are infinitely many possible Feynman diagrams that can contribute to the interaction. But the amazing thing is that when you add up all these diagrams, when you sum over all the possible ways the photon and electron can interact, the mathematical result turns out to be exactly equivalent to the classical description of reflection. The quantum calculation gives the same answer as Maxwell's equations. This is why we say that quantum electrodynamics is consistent with classical electromagnetism. Actually, let me be more careful there. Classical electromagnetism is the limiting case of quantum electrodynamics. It's what you get when quantum effects are small. In that limit, the quantum calculations reduce to the classical equations. Now, why are quantum effects small? It's because light and matter interact very weakly. The strength of the interaction is characterized by something called the fine structure constant, which has a numerical value of about 1 divided by 137. It's a small number, so most of the time, most of the quantum corrections to the classical theory are tiny. They're too small to detect with ordinary apparatus. This is why classical physics works so well for most practical purposes. But let me tell you about a case where quantum effects become important. What happens if the light is very intense? Or what if we're dealing with very short wavelengths like X-rays? Or what if we have many photons all trying to interact with the same electron? In these cases, the approximations break down. The quantum effects become important, and you need the full machinery of quantum electrodynamics to make accurate predictions. But for ordinary visible light reflecting from an ordinary mirror, the quantum corrections are tiny, and the classical law of reflection is an excellent description of what happens. All right, let me tell you about one more thing because I think it's important. I've been talking about a smooth mirror, a flat mirror, where the surface is smooth compared to the wavelength of light. What happens if the surface is rough? If you have a surface that's rough, if the roughness is on the order of the wavelength of light or larger, then light doesn't reflect in an organized way. Different parts of the rough surface reflect light in different directions. The reflected light goes in many different directions at once. This is called diffuse reflection. You don't see a sharp image in a rough mirror. Instead, you see the object, but without a distinct reflection. The extreme case is a perfectly rough surface, where every small bump on the surface scatters light in a random direction. In that case, the light is scattered in all directions equally. The surface looks bright from all directions. It's like a Lambertian reflector. But here's what's interesting. Even in diffuse reflection, the individual photons still obey the law of reflection. Each little microscale bump on the rough surface reflects light according to the law of reflection. But because the bumps are oriented randomly, the overall reflected light goes in random directions. So the law of reflection still applies to each little piece of the surface, but the macroscopic effect is diffuse reflection. This is a beautiful example of how a microscopic law, the law of reflection, can combine with randomness to produce a very different macroscopic effect. Now I want to talk about one more aspect of this because it connects to something very fundamental about the nature of light. I mentioned earlier that light has both particle and wave properties, but I haven't really explained what this means very carefully. You see, when light is described as a wave, we imagine it as an oscillation that extends through space. A wave has properties like wavelength and frequency. Different wavelengths correspond to different colors. Wavelength times frequency equals the speed of light. This is the wave picture. But light also behaves like a particle. The particle of light is called a photon. A photon has energy equal to Planck's constant times the frequency. It has momentum equal to Planck's constant divided by the wavelength. When light interacts with matter, it interacts in discrete packets, individual photons. Now here's the thing, these two pictures aren't incompatible. They're two different aspects of the same reality. Light at any given place and time can be described either way. If you ask, what is the intensity of the light at this location? You're thinking of light as a wave. If you ask, what is the probability that a photon will be detected here? You're thinking of light as a particle, but it's the same light. The wave description tells you about the probability amplitude. The probability amplitude is a complex number whose absolute value squared gives the probability. The wavelength and the frequency of the wave encode information about the momentum and energy of the individual photons. So when light reflects from a mirror, you can describe it as an electromagnetic wave, a ripple in the electromagnetic field bouncing off a conductor. Or you can describe it as individual photons, each with definite energy and momentum, being scattered by electrons in the conductor. Both descriptions are correct. The wave-like description is more useful when you're dealing with ordinary mirrors and ordinary light, where there are lots and lots of photons. The particle description is more useful when you're dealing with very weak light, where individual photons matter. But for understanding what's fundamentally happening at the deepest level, you need quantum electrodynamics, which incorporates both the wave and particle pictures in a consistent way. Okay, so let me summarize what I've told you because I've covered a lot of ground. The question is, what happens when light hits a mirror? The answer is, light interacts with the free electrons in the mirror. The oscillating electromagnetic field of the light pushes the electrons back and forth. These oscillating electrons, being accelerated charges, radiate new electromagnetic waves. The properties of the mirror material and the boundary conditions at the surface determine the direction in which this new radiation travels. For a smooth mirror, the mathematical result is that the new light travels in a direction such that the angle of reflection equals the angle of incidence. This can be understood from the principle of least time, which states that light takes the path between 2 points that minimizes the travel time. It can also be understood from quantum mechanics, where light explores all possible paths and the classical path survives because of constructive interference. The image you see in a mirror is not a real object behind the mirror. It's a virtual image created by your brain's interpretation of where the reflected light came from. Your brain assumes light travels in straight lines and uses the law of reflection to trace the light back. The conclusion is that there must be an object behind the mirror. In reality, there's nothing behind the mirror. The photons that hit your eye came from an object in front of the mirror, bounced off the mirror surface, and entered your eye at the reflection angle. Your brain reconstructs the trajectory backwards and places an image at the mirror symmetric position. This is what happens when light hits a mirror. It's not a bounce. It's an interaction between light and matter, ultimately governed by the laws of quantum electrodynamics, but in the classical limit, well described by the law of reflection and the principle of least time. And that, I think, is a much deeper answer than light bounces off the mirror.